Otherwise, I think that is about it. So I'm going to go ahead and introduce our presenter, Matt Christie. Matt is an associate director for TRC. He consults to utilities and state agencies nationwide on residential energy efficiency and decarbonization policies and incentive programs. He has devoted his career to advancing all electric and zero net energy residential buildings into the market. So I think you can go ahead, Matt, take it away.
All right. Thank you so much, Ginevra. Thank you, Michael, and thanks for everyone for being here tonight. As Ginevra said, my professional work, where I'm coming to for this is I consult utilities. I'm not trying to sell you anything. I just study this topic deeply and work with this topic professionally, and believe that very strongly that heat pumps are entirely ready now as a technology to be the primary heating technology for residential homes in Vermont. And we're ready to make the pivot, and the technology is there. And my job today is to explain that and hopefully convince you of that yourself and maybe spur some people to make some changes that way. I'm also a member of the Stratford Energy and Climate Committee, which is what this slide is from. I did a similar presentation as this to town residents in Stratford a couple of weeks ago, so I'm repurposing that same slide deck. Walk through sort of what I'm going to go over. I'm going to take questions at the end through the chat, as Ginevra said, but first, just why heat pumps, sort of the basics, the broad, why is that such a hot topic? Why are we talking about it now? Why do I care about it and study it and work with them? A little bit of the basics of heat pump operations and how they work, so you understand the physics and the engineering of how they function a little bit better maybe, which can help, at least helps my brain, the style that I learn, to understand how it works in my home, to feel more confident and comfortable. A little bit about system design options and how a heat pump might fit into your house or into your life. And then a little bit about heat pump myth busting and just talking about some of the stuff that's out there that is no longer correct with modern heat pumps and some of the technology changes that have occurred in the last 5 or 6 years.
I'm seeing a note, Matt, just to interrupt, that someone says, can you turn up the volume some? Which people can do on their individual computers, but maybe they're not hearing you as much.
I've moved the wand. Does that sound a little bit better to you, Ginevra, who's hearing this directly, or about the same?
It sounds a little loud. Yeah, it sounds louder to me, but I could hear you okay before. So yeah, thank you.
Fair enough. All right, why heat pumps? So for climate change, it's the only efficient zero carbon home heating technology option. And by the way, I'm including both air source heat pumps, which is going to be the root of today's conversation, and also ground source heat pumps, sometimes called geothermal heat pumps. Same technology, essentially, just a different source of heat, whether it's coming from the air or coming from the ground. But heat pumps broadly are really the only efficient zero carbon home heating technology option. And one might say, it's electricity coming off of the grid, which isn't exactly zero carbon yet, but that's true. But it will be. It's getting there. The current Vermont grid is about 66% renewables. By 2032, it's going to be 75% by law, by statute. It's going to get to 100% at some point. We don't know exactly when. It might accelerate faster than you think. But in terms of planning out low carbon, comparing it to any of the other options, including wood heat, it is the lowest carbon technology. Number two, it has lower operating costs in most cases in terms of fuel costs, utility bills, and maintenance. It's almost always better than oil. It's almost always better than propane. If you have natural gas, which most of the people on this call probably don't, given this is Woodstock and regional, that one can be more comparable in price, and sometimes the electricity costs can be higher for markets that have. If you're thinking about a home up in Burlington or somewhere else that has natural gas, that can be a little bit closer of a price comparison on utility bills. It has competitive purchase costs, a little bit situational depending on what you're trying to do to the home and if you're doing a direct swap out, but the price point right now for a good modern heat pump is entirely fair and matches pretty closely to replacing an oil system or replacing a propane system. You also get the benefit, you get heating and cooling out of one piece of equipment. So if you got box air conditioners, window air conditioner units, or you have central air conditioning, you can replace that as well, and you get heating and cooling out of one piece of equipment maintained. And if you are thinking about adding cooling, don't add air conditioning at this stage. add a heat pump and at least get some of, even if you add it just for the cooling and you only get some of your heating load covered by the heat pump, that's entirely worth it. You'll save on your utility bills. It's a great move. This bullet does not apply to this market. Again, I stole some of these slides from slide decks that I did in other places like upstate New York. But if you can eliminate having the gas hookup if you're on a natural gas system entirely, not pay any gas bills or the gas hookup fee. And then if you go ductless, you can also eliminate the duct costs. Setting up ducts in a home can be one of the pricier parts of redoing a heating or cooling system. Ductless systems work really well, and you don't have to deal with ducts, and you get that cooling benefit and the heating from your heat pump. And then health and safety. There's no in-home combustion. So almost all of the heating that we've relied on over the last X hundred years, you're burning something in your house, which has safety issues, both indoor air quality from particulate matter coming off of that fire and fire safety. Obviously, the modern ones that are in a condensing furnace, or boiler in the basement, that's pretty safe in both of those, but it's not entirely safe, and heat pumps eliminate both of those safety issues. All right, why now? Heat pumps have been around for a long time. Like, why is it a hot topic now? At least it's a hot topic in my world. But why are you maybe hearing more and more about heat pumps in the electrify everything kind of conversations about sustainability? First off, heat pump technology, it's really improved a lot. A lot in the last 5 years. There's sort of a new product change about 15 years ago, and in the last 5 years, that's really kind of accelerated. The cold climate heat pumps are for real. They're here, they're very functional. They can work down to -30 for some product lines. They work up in Alaska, up in northern Canada. The products you buy here, you don't need to get it down to -30. It doesn't matter. You only really need to get, most of the ones that they even stock here, you could purchase and you'd want to consider go down to about -15 operating, and that's plenty, even on the coldest days in Vermont in our climate zone. And they'll operate all the way down to those temperatures. And there's also a lot of design options to fit your home and need. So you can really sort of mix and match and figure out a heat pump solution that works for your home. And we're going to go into a lot of those kind of design considerations. It's a lot different thinking than thinking about traditional oil or propane or sort of a wood or central plant-based heating systems. You can also get a lot of rebates and incentives from Green Mountain Power and Efficiency Vermont. And then the big picture, and probably most of you are here for sustainable wood stock, so I don't need to preach this, but we're really running out of time to limit climate change and some really bad societal harm. And residential heating and transportation, those two uses, your car and your heating, is 76% of Vermont's carbon footprint. Residential, just our houses. So it's about 50-50 between car and house, ballpark. So knocking out half of that by switching to heat pumps is a big thing that you can do for the carbon footprint of your life and for Vermont and for the world. Gonna get into the taxonomy just a little bit here, some of the terminology. Again, I'm talking about heat pumps broadly, or heat pumps broadly are a great technology. This slide kind of narrows in on them. Today, we're really going to focus on the ones in orange and yellow in this graphic. So residential grade heat pumps, you can do hot water or you can do space heating. There's sort of two different technologies typically. The heat source is either air source or ground source. You can do air to water. I'm mostly going to talk about air to air. Air to water does exist, but they're not very tuned yet for cold climates. There are a few products out there, but that's not the focus of today's conversation. Ground source also are great. They're entirely tuned to cold climates. They're a little bit more expensive. They're an amazing whole house solution. They've got a little more durability to them and longevity to them maybe, but also not going to be what I focus on today. Both air to water and ground source could directly feed your hot water at the same time, where a typical residential space heating air source doesn't do both at once. Then once you get to this final column, this distribution column, sort of how do you get that heat into your home? What makes air source heat pumps interesting, there's a lot of options there. You got mini splits. You have one outdoor unit serving one indoor head, and you're producing heat. You're pulling heat out of the air outside, running it, pumping that heat, that capture heat through refrigerant lines, and then you're releasing that heat inside is the basic operational principles. We'll go into that in more detail. But you got one-to-one, one outside unit, one inside unit, you're producing heat. Multi-split, you have one outdoor unit and it's serving multiple heads inside, and these ones are all in their own zone. So their own thermostat, they're producing heat when that, the living room's calling for heat, the master bedroom calls for heat. They're kind of operating independent of each other. And that's the term multi-split. You can do centrally ducted, where you have a unit outside and that feeds a ducted unit on the inside, and that through the ducts, through a forced air, forced air, you can push that through the fan all the way around your house, dumping it where it needs to go, pulling air in where it doesn't. Works just the way a central AC or central air works, for those familiar with those. There's not a lot of central air up here in northern Vermont, but if you've lived elsewhere, and there's a few houses that do it. You can definitely do ducted. It's a great way of distributing the heat. And kind of unique to duct, there's also short ducts, where if you have just 2 or 3 bedrooms right in a row upstairs and having an individual head for each one is overkill, you can just run a really a short duct across those 3 and serve just those 3 bedrooms off of one kind of indoor unit or indoor head. Runs 3 bedrooms through a short duct. PTHP is packaged terminal heat pumps. That's another technology that's not quite ready for cold climates, but it's sort of a valuable use for multifamily products and multifamily homes, and some single family once it does mature and become ready for residential in cold climates. All right, so I keep saying cold climate heat pump. I'm going to narrow that in and what that term means. There's confusion around the term and conflation in the term. The big category that I'm talking about is air source heat pumps. That's a heat pump that pulls heat out of the air outside and brings it inside through a vapor compression cycle. A subset of that is a variable capacity heat pump. So this variable capacity, it means it can modulate how much it's pumping heat. It can pull a lot of heat, it can pull a little heat, it can change that. It uses an inverter-driven motor compressor to do that. It's different than sort of old school heat pumps that have 1 or 2 speeds. And that's a variable capacity heat pump. A subset of those are called cold climate heat pumps. And there's 2 organizations, NEEP and NEA. NEEP is the Northeast Energy Efficiency Partnership. NEA is the Northwest Energy Efficiency Association. These are regional energy organizations. I work with both quite a bit. But they each maintain a kind of a qualified product list of cold climate designated heat pumps that have a specific performance requirements to be listed, and they list on theirs. And most of the programs, Efficiency Vermont's program, the New York State Clean Heat program, the Mass Saves program, all the programs around here that incent heat pumps require that they be listed as a cold climate air source heat pump on NEEP's website and on NEEP's database. And that's kind of your test to ensure that it is engineered to work well in our cold climates, or pretty well. Although I will say there's a lot of variability in quality in the overall application quality, even on units or products that meet those qualifications. Variable capacity heat pumps are also known as some other terms you may have heard. Inverter driven, that's because that's the sort of the core technology that's underneath them. Extended capacity, because that's the same technology that gets you good performance in cold climates, actually helps your performance in hot climates and cooling as well. If you're trying to put these in where there's a high cooling load, there's not really a high cooling load here. There's some. It's valuable to have. It can be really nice to have air conditioning in the middle of summer for those couple of weeks. Extra performance, extreme climate, and then each of the manufacturers kind of have their own trade names. Hyperheat, Aurora, Halcyon, Maxheat. These are kind of some of the trade names that Mitsubishi and Daikin and Fujitsu and Bosch and all these companies that make these products might apply to their own product line. All right, I'm going to walk through sort of some of the engineering principles and the physics principles of how a heat pump operates, what it's actually doing in the home. The first thing to really grok and know is that heat pumps do not generate heat. They don't create heat themselves at all. All they do is move it. They take it from one place and they move it somewhere else. So where does that heat come from? In the winter, in heating mode, the heat comes from the outside air, which is essentially heated by the sun, even when it's really cold outside. So the heat, whatever temperature it is outside, the unit will make sure that it is able to capture some of that heat There's always extra heat in the air, right? You're not out of heat until you're at 0 Kelvin, it's negative 300 Celsius, whatever that is. So there's always some heat out there. Now, capturing it gets harder and harder, but you're stealing heat from the outside, you're pumping it inside. So you use some energy, heat energy from the air outside, combine it with some electrical energy from the grid. The electrical energy from the grid, all it's doing is running the components of your heat pump and doing that compression, doing the work to move and pump and capture that heat and deliver it inside. And it does that at about a 3-to-1 ratio for seasonally for most modern heat pumps, which makes it 300% efficiency, which conceptually breaks the rules of physics. You can't be 300% efficient. You can, because you're not actually using the heat, the energy from the grid to produce it. You're using energy to steal heat from the outside, and the heat from the outside is free. Right? It's just there. It's coming from the sun. It's always there. And then in the summertime, it does the reverse. It takes heat from the inside of your house and pumps it, uses a little bit of electricity from the grid, and dumps it outside. Also in the ballpark of 300% efficient. So what's it actually doing? It's using a vapor compression cycle. So it pumps refrigerant, which is a special chemical compound that's really fine-tuned to do this. It pumps a refrigerant in a closed loop through a hermetically sealed set of pipes. It pressurizes the liquid to deliver heat, squeezes the liquid to make it hot and deliver, just like a pressure cooker. You add pressure to something, it heats up. Squeeze the refrigerant, it delivers heat. Release the refrigerant, release the pressure, it collects heat. And you just run it around in a circle. You collect heat from the outside at low pressure, you squeeze it and you dump it indoors to deliver heat. And then in the summer, you flip a little switch, or it flips a switch on its own inside the system, and it just does everything in reverse order. It literally just goes backwards and goes the other way, where you decompress, you depressurize to collect heat from inside your house and cool your house off, and then you compress it to dump it outside. And the nice thing about variable capacity heat pumps is they can modulate how they do that, right? They can ramp up, they can put out a little bit of heat, they can put out a lot of heat, and they can change and they can vary. They do it really fine-tuned through pretty sophisticated machine learning and algorithms on the inside. So what that means for comfort and control is when you have an inverter-driven heat pump, these variable capacity heat pumps, this is a graph of temperature versus time. So this is your house. You have your thermostat set, somewhere around here, say 70 degrees, 68 degrees. You want it to warm up. Your house is too cold. Your heat pump can go, oh, I need to catch up, and it compress really aggressively. Catch up, and then it says, oh, I've caught up. I can slow down. I can temper back, and it sort of tempers back. It doesn't provide as much heat, and it lets it drift a little bit down. It goes, okay, I should turn back on, produce some heat. And it can kind of just do this nice, mellow, on-off, slowly, like long 20-minute, 40-minute cycles of energy going on and off, and keep your house nice and smooth and really temperate. An old school heat pump that doesn't have an inverter, it has one mode. It goes hard and heavy and only. So it'll pump. It'll actually intentionally overshoot because it knows it has to. And then it'll let you drift for a long time. And then it goes, okay, I'll turn back on. And it pumps and it pumps and it pumps and it overshoots. And then you drift. And so you get this wasteful energy. You also get less comfort. You don't get the same level of control. Going back briefly to NEEP, the Northeast Energy Efficiency Partnership, they have this qualifying product list. These are the rules to get on it. You have to be variable capacity. You have to have a good efficiency rate, decent efficiency rating. These are not particularly high, but decent overall efficiency rating. This is the one that really matters. You have to have a high efficiency even at 5 degrees Fahrenheit. So your coefficient of performance or your efficiency rating has to be at least 175%, 1.75, even at 5 degrees. That's the clincher that basically says, I work in cold climates pretty well. And then you have to report your data to NEEP and maintain it and ... And NEEP maintains the list, publishes the data. You can go there right now and peruse it for free. It's a great source. Learn more about the heat pumps on the market. All right. I'm going to get into some weeds on the different design options for your house and how it might fit your home. And I'll start by just saying it is conceptually different than designing with and thinking about providing heat with a oil furnace, oil boiler, propane furnace, a central plant heating system. For those fossil fuel systems, you basically have a really dense heat source of a fossil fuel that you burn and create a ton of heat in one location, in your furnace, in your basement, or wherever you have it. And then the entire job of the art is, make sure you're producing the right amount. Your burn is enough to heat the house at the coldest of cold days. And then the job is, how do you distribute that heat around the house, either through ducts and forced air or through radiant hydronic. Those are your hydronic baseboards that pump the hot water and get around a radiant floor, pumping warm water into your floors, into pipes that go through your floors. And that's the art, that's the game. But fossil fuel systems, they just burn they got one setting as well. They're just like old school heat pumps. They just burn a lot of energy at once, and then it's, can I distribute that efficiently? And they do it pretty well, efficient-wise, but not well enough. And they're also burning fossil fuels, distributing carbon. So we're trying to get off of that. First two concepts, displacement versus replacement. So displacement is what a lot of homes are doing right now, right? They have an oil boiler, it's doing hydronic or an oil furnace, they're heating their home, but they want to just use a little bit less of it. And so they put one heat pump head in their living room, and it works really well. It delivers all the heat they need for their living room at any time of the year or most of the year. They're only trying to heat a portion of the home. They're only trying to cover a portion of the load, and they leave that oil boiler intact, and it runs as backup. It runs when it gets really cold out, or it runs, even when it's, moderate out, to get the heat up into the bedrooms because there's no heat pump heads up there. Very common. And a displacement system, even a fairly small system, because a lot of the hours of the year that we're heating aren't that cold. And one heat pump head in the living room can cover most of the house. Enough that heat drifts upstairs. And so in April, when it's 50 out, 40 degrees out, or 35 even, you're fine on just the heat pump. You won't need that oil system going. So this can cover a lot of your load without a lot of effort and without trying to have to think through all the detailed speccing of trying to make sure your heat pump can cover everything, which is a little bit harder to do and takes a little bit more planning. So great option. Replacement heat is, I'm trying to cover the entire house in heat pumps. I might have backup at my preference, but it's optional. A lot of people say, what happens when the electricity goes out and your heat pump doesn't work? And my answer to that is, what happens with your oil furnace when the electricity goes out and your oil heat furnace doesn't work, right? You can't pump the water, you can't blow the air. When the electricity goes out, no matter what you're heating on, unless it's a wood stove, you're not getting heating out of any system except for a wood stove when the electricity goes out. The good news is houses drift very slowly on temperature. So you can lose energy, you can lose power for a few hours, 5-6 hours, and only lose like 1 or 2 degrees of temperature in your house. It's worse if you're not well insulated. So come to Green Drinks next month to learn about weatherization. I fully endorse weatherizing before you do heat pumps. But there you go. All right, next set of concepts for design intentions. Are you trying to zone the house? Or you want to have different thermostats controlling different zones that can have their own temperature set points? Or you want to do the whole home all at once with one zone and one central system that controls it all at one temperature? Basically, a small, simple house, just do one zone. You don't need to zone it. You can zone it, and having a bunch of little mini zones with ductless one-to-one mini splits, that works really well. Zonal, more for complicated homes, but larger homes, each zone has its own control. That's sort of think about how you want your house to operate, what matters to you. Doing it zonally means you could do things like let the living room and the other rooms drift, and just keep your bedroom warmer or whatever it is. Next design intention, sort of ducted versus ductless. So in the ducted system, talked about this already, you're distributing heat to each room through ducts. This is really best for like full homes. This is overkill if you're trying to do partial, but it's not necessary to do whole homes. I see hundreds of whole homes in the programs that I'm managing in New York that are going ductless, a bunch of ductless heads here and there, one in the living room, one in the master bedroom, one in the, the TV room, and you're done. But ductless systems kind of look like that. They got some kind of indoor unit, and in a ducted, they're obviously a little more hidden as well. Then within the ductless world, you can do mini split or multi-split. Mini split again is one head per outdoor unit. A lot of people, as I said before, install multiple mini splits. So a bunch of 1-to-1 ratios, one unit outside and one unit inside, and 3 sets of those, or 4 sets of those covering an entire home. 2 sets of those. 1 set is fine for a small house, 1,200 square feet, 1,500 square feet. You might get away with 1. You might want 2 just for distribution purposes. Multi-split is 1 unit outdoors, and then it splits and different thermostats control different zones. You really be careful with the sizing of these. And I advise, and we advise in the programs that I run, that you never have more than 3 zones connected to 1 outdoor unit, or you're going to get a big mismatch. If 1 zone is calling, but the other 2 aren't, you can't produce a small enough amount of energy to serve that 1 zone. And your system does something called short cycling, which means turning on and off rapidly. As it fires up to provide the heat, and it goes, oh, I finished my job. 90 seconds later, it turns back off. And that's really inefficient operation. You lose a lot of your efficiency if it's doing that a lot of its operating time. The other thing that's really nice and unique about heat pumps is you got all these options. It's very modular, right? You can mix and match. You can get, a couple short duct runs. You can do combinations. You can do a ductless unit downstairs and then some short ducts upstairs to cover all the bedrooms. You can kind of, you can play with, you can't do that with a fossil fuel system, right? Fossil fuel, you have a central plant, and then you just got to figure out how to distribute it everywhere. Heat pumps, you can be a lot more playful and thoughtful. Now, the flip side of this is that the HVAC contractors, the heating contractors that are learning heat pumps anew, it's kind of new for them to be able to consider all those options. So it's really important to think through what the options are and make sure you're thoughtful in your design and matching your load and matching your home's need. And that takes some experience to do well. Some other design considerations, especially out here in the northern Vermont or central northern Vermont, snow protection. If you're doing heat pumps for heating, make sure your heat pump is off the ground. You probably want at least 18 inches around here, maybe even 24. Make sure it's protected. You also want to make sure it's protected from above. That's not going to get if you have a standing seam roof, it's not going to slide and bury the thing. A lot of contractors forget this because they've been thinking about heat pumps as a cooling technology first that maybe helps out in heating as a side gig. And they're like, yeah, we don't care. But if you're thinking about heat pumps for heating, you got to make sure this thing does not get buried in snow. If it does, it will not operate, and you can damage the equipment if it tries to run and it's clogged up with snow or ice. Placing on the gable ends of a home, that's the side that has the little triangle. That helps a lot, avoids the roof dump issue entirely. It's always best advised if you have a good location that works. Be thoughtful about where it is for wind protection and getting leaves clogging it up. There's always, a lot of homes have a corner where all the leaves seem to gather. Don't put the heat pump right there. Don't let it get gathered upon to clog it up. Then you also want to consider the line sets. Ideally, you're within 25 feet where the unit is, going from the unit outdoor to indoor for your line runs. It can be greater than 25. If they go longer than 25, that takes a little bit more engineering calculation and you lose a little bit of efficiency. Not a lot, just a little bit. But if you can keep them close, that's the best principle. And then noise vibration. These things have modernized a lot, and the noise vibration concerns are much more mellow than they were 10 years ago. And maybe if any of you dealt with heat pumps in the past, way better than they were in the long ago. But there is some noise vibration, so you probably don't want to mount these like on the outside right next to your bed or right next to your favorite quiet reading corner. Try to avoid that if possible. Right, I'm going to go into some myth busting. So myth number 1, heat pumps are not suitable. They don't work in cold climates. You'll actually hear this even from HVAC contractors that sell heat pumps. It is no longer correct. It was entirely true 10 years ago, maybe 15 years ago. The cold climate heat pumps right now, though, they are great. They can go well below 0. They're totally functional. You get the right product to deal with your entire winter in Vermont, in Woodstock or the surrounding areas. Myth number 2, heat pumps are only useful for little sort of niche applications, mudrooms, additions, sort of ancillary heating. It's not really a technology you should consider for your entirety of your house, right? It can't keep up. It's not really, again, not true. It was true. This was true 10 years ago, and that reality is still in the mindset of a lot of people, even those who install heat pumps and work on HVAC systems. But modern heat pumps can provide heat for a wide variety of settings. You can still do that backup thing for a mudroom or an addition, or just like one component of a room, like I talked about before, as a displacement scenario. But you can also do an entire massive house with multiple zones, everything in between. I'm helping to work on a program in upstate New York, and we're doing whole home applications on thousands of homes a year right now. Probably a couple hundred a month is what we're doing right now across upstate New York. Similar climate to what we have, the only heating system in the house. They very much work. Myth number 3, they don't work for older homes, right? Heat pumps are only good if you have a really well insulated, modernized, weatherized home. So reality, yeah, older homes are harder, right? Older homes take a bigger heat pump. They can be much more expensive to convert. An old leaky home with bad insulation. So always, if you can, even with a modern home, look at weatherization first. Look at insulation first. Look at improving your insulation. If you can bring down the size of your heat pump. You can make the engineering challenge a lot easier. But even in an older home, it's tough to do propane and oil too. Same thing. You need a bigger system. You need to oversize your radiant hydronic boards everywhere to take up the entirety of your sidewall. But you can do anything. Improving is valuable, but you can do an old farmhouse. Myth number 4, they're ugly. They're not ugly. They blend into the background. You might notice it at first, but honestly, these things just blend in. The other option is they also make, they make floor units. They make ceiling cassettes that just embed in your ceiling. It just looks like an air grill, but it's actually a ductless head that's embedded. Those are a little more expensive. You got to cut away and put them in. Expensive for installation, not for product cost. But surveys of ductless heat pump owners, these have been very popular in parts of the country. Oregon and Washington, they've been around for decades. They're sort of a very prime. No one notices them. They're just sort of nice and pretty in the background. They fade away super fast. Heat pumps are noisy and uncomfortable. So similar, I talked about this before. They're barely audible now. Another myth that I didn't put in there, maybe I should have. I don't think I put it in. Is there another slide? I do have one more slide. Maybe that's it. Oh no. Another one we've heard that I didn't put in my deck is that they blow cold air. This is a misperception. Heat pumps operate a little bit differently. So with an oil or a propane, the heat that they produce is a really dense heat source. So the air that's blowing out of them is like 120 degrees. And if you're next to the air output of a forced air, oil, or propane system, it feels like this blast of heat. You're like, oh yeah, I'm getting heat. A heat pump is designed to operate steady at moderate heat temperatures. So it's pushing out like 90-degree heat at a nice, low, steady pump. And when you're standing under that, it doesn't feel hot because the air is moving and you get that convective heating or convective cooling aspect of moving air. And it might not feel particularly warm to you, but it is. It's 90 degrees, it's 85 degrees, it's hotter than your indoor air temperature, and it's slowly getting out across your house. And so there's a perception that they blow cold air, but the reality is they're blowing warm air and they're doing their job really well, and they do that. And that's how they stay efficient, and more efficient than your blast of hot air you might have become accustomed to for those that use forced air furnaces with oil or propane. Myth number 6 is they cost too much money. They're too much to put in, they're too much to operate. Again, home to home, the full picture of purchase is really dependent on the home and the application, right? You can put in really expensive heat pump systems. You can put in really expensive oil or propane systems. But overall, right now, lots of studies have shown that heat pumps save money over time on an annual basis and often have lower installation cost. Against oil, the ballpark right now is that a heat pump operates at about 65% of the fuel cost as oil. Against propane, it's something like 70 or 75% of the fuel cost of propane. So operating costs at fuel, if they're designed properly, it's almost always a win. Install cost, again, that's really dependent on your home situation. And with that, I'm going to stop for questions. And I'll also, I'll stop for questions. Ginevra and Michael, thanks.
Hi, thank you so much, Matt. I learned
Thank
a
lot.
All righty. Well, folks can go ahead and keep typing questions here in the chat or on Facebook in the comments section, but we're going to get started with what we have here so far. So the first question is, can heat pumps work if you have radiators?
So the heat pump would replace the radiator. So radiator is either hot water or steam. Radiators, it's a central plant that's pushing that heat through steam or hot water to a radiator at the side of your house. Yeah, you'd replace it. And there's actually great little floor unit heat pumps there. Let me try to find one, an image of one. They look kind of like this. They kind of look like a radiator. And they can sit underneath a window and you can just replace it and they put out your heat.
Okay, so the next question, I guess, is related. What if you have a water system for heat already? What would you do?
Do you have a hydronic water system? Yeah, so right now, the way is keep that as backup and do air source heat pumps around the house. That's one option. Remove it entirely and do heat pump backup, heat pumps around the house. But right now you can't tie directly into an existing hydronic distribution system with cold climate functional heat pumps. There are technologies on the way. So there's at least 3 startups that I've been working with that are doing air to water heat pumps that work well and efficiently in cold climates that produce hot water that's hot enough to work in a standard hydronic distribution system. They're not on the market yet. I have no idea when they're going to make it. A couple of years out, I have no idea what their price point is going to be. But there are some things kind of in the R&D pipeline that would resolve that and get there. We'll see how well those actually materialize and when. If you're doing a water-based heating system and it's a radiant floor, then there are some products that work now with that. The reason being is that the water temperature that you use for a radiant floor is only about 80 degrees. It's much cooler. The water temperature you use for hydronic baseboard is like 170, 180 degrees. And there's some air to water heat pumps that can do efficiently in cold climates get to 80. They can't get to that 170 right now. So there is a differential, and those products exist and are on the market. And you could probably find them.
Thank you.
Thank you, Matt. The next question is, you said that air to water is not tuned for cold climates. What does the future look like for that?
It's kind of a question I just answered, right? So yeah, they can't get up to the high enough water temperature for that circulation to work for people's hydronic distribution systems. So as I said, technologies are coming. We'll see. If you're doing radiant floor, then there are technologies on the market that are available. There are products on the market from a bunch of companies that can do that right now efficiently in cold climates.
So Matt, the next question is, why are the ductless units always mounted high on walls?
Yeah, that's just for airflow. The best way to get the heat, because they're blowing air out, throwing that air across the top of the room. I know heat rises, but it circulates. It gets some eddies. It moves around. And they're not all that way. They're also, as I showed in that picture, there's the floor units. Looks like a little radiator. You can put them sort of underneath a window is a great spot for them. And they'll blow air from the floor, from that area, that region, that lower side of the wall and blow it out. The reason they're that way is that heat pumps were designed for cooling first concept over the last 40 years of heat pumps existing. And sort of that historical reality has stuck, right? So most of the designs out there that are being piggybacked upon or that, they go up high in the wall. But there are floor units totally available from all the manufacturers.
So yeah. they were originally designed so that they would blow cold air, which would then sink into the room.
Cold air flies across the room and then sinks everywhere. But the distribution, you don't get a lot. The stratification issue of having all the heat, sort of staying up against your ceiling, it can be a problem if you have like a big vaulted room, right? 2-story or something, or big arched ceiling or cathedral ceilings. It's not really a problem at all in a standard 9-foot, 8-foot, 10-foot ceiling in a normal during heating season.
The next question is really similar, and you've gone over a couple of these, but if you have any other options, they're asking what options are available for physical indoor placement. So if there's anything you feel like you've missed.
Yeah. If you got a basement, you can do short ducts along in the basement, or ducted systems in the basement that get room to room and come up from below as a register. If you don't have if you have an attic, you can do ducts up there. You can do ducts inside and kind of hide them in chaseways. As I said, the ceiling cassettes, you can cut away your ceiling and it looks like a register for a forced air unit. Even though all that's what's up there, they run refrigerant line to get to that unit. It pumps your air there. Yeah, but those are pretty much the aesthetic design options.
Thank you.
Okay. So the next question, Matt, is I heard heat pumps can pull out moisture in the air or act as dehumidifier. Is that true?
That is entirely true. Yep, they do, because that's how they operate. Yeah, so they especially, they'll pull moisture out of the air, same as air conditioning does, frankly. Yep, you'll see as they're operating, they have a condensate line that lets that water drip outside. I should caveat, they do that in the summer the most. Like they don't do that when they're running in heating mode. They're actually dripping moisture outside because it's where the heat is being stolen from that it condenses. Okay. So in cooling mode, you're pulling moisture out of your air inside and it acts as a dehumidifier. In heating mode, you're not doing anything to the humidity in the house.
All right. Next question is, well, understandably, the cost depends on size of house and what type you choose. Can you give a range of what this could cost to install?
Yeah. So whole home solutions in New York for residential homes that are doing heating systems to cover the entirety of the house with intention to be in the entirety are anywhere from $8,000 to $30,000. And above 30,000 for like really, complicated mansion, whatevers. But that's your ball. And for ground source, it's about 25 to 30,000 to do a whole home. Maybe lower on a smaller house, but ground source could be overkill for a smaller house.
And there are also incentives, correct, from Efficiency Vermont?
Correct. And I don't have those memorized because I don't work enough in the Vermont market on the incentive side. Right. I mostly work in New York and California and Oregon.
Yeah. So if folks want to go into just Google Efficiency Vermont, you'll see some incentives and you can look at the pumps there for incentives.
They're pretty good right now, is what I've been told.
So another question, Matt, is can one put heat pump air through an existing air duct system?
Yes, definitely. If your ducts were sized for cooling only, then they might not be big enough to manage your heating load in our climate. But if you have ducts that are sized and done for a heating system, an oil or a propane heating system, you can tap right into them and repurpose them. You may want to do, check them out, make sure that they're well sealed and they're insulated, all that stuff. It's always good to recheck your ducts, but
So as long as your ducts are in a row, you're all set.
Yeah, get your ducts in a row. And don't use duct tape on ducts, ever. Not designed for that.
I'm ignoring this tangent. How long do heat pumps last usually?
Yeah, they're a good mechanical equipment. They're 15, 20 year. If you get unlucky, you can just like a car, you can get a little bit of a lemon, but maybe 10 if they're overtaxed and they weren't designed well. But yeah, 15 years is 15 years is the effective useful life that regulators use when they're qualifying the benefits of a heat pump for a utility program. So that's telling. Like that's what the Public Utility Commission says the useful life is.
So next question is, does the humidity, meaning of the ambient temperature or ambient humidity, does that affect the efficiency of the heat pumps?
Not particularly.
All right. And then can the pumps be under a deck?
Yeah, great place for them. Snow protected. Outdoor unit under a deck is great. They need a certain amount of air circulation around them, to move. But most decks are, if it's like a really low, if you have like a porch, right, you only have a couple feet of gap, you're not going to get enough airflow through there. But if it's actually a deck, yeah, great spot.
Do heat pump systems use HEPA filters?
Yep, they've got a filter in there to pump the air, and you got to clean that filter every 6 months, is advised. It's really easy. You slide it out, you wipe it. It's like clearing the lint screen on your dryer. Slide it right back in.
Great, thank you. What are the largest capacity units that meet the cold climate certification? And then this person in parentheses says they're thinking of commercial use.
Yeah, so the ones on the cold climate list are by definition residential scale heat pumps. Commercial heat pumps, they exist, they can be really powerful, right? And most of the time they use a bank of compressors on the outside that work in tandem with each other. On the cold climate heat pump list, which is again defined as being a residential grade product, the biggest they get is about 60,000 BTUs, so 5 tons in one system. But again, if you have a higher heat load than that, just have 2 of them, right? Have 2 30,000s or 2 40,000 BTU systems.
Okay, thank you. Is it best to place the outdoor units in the shade of a deciduous trees, so they're in the sun during the winter?
It almost doesn't matter, right? Because they're pulling from the ambient air, and it feels cooler in the shade and in the sun, but that's mostly radiative, like radiant heat. You feel it on your skin, but it's not actually the air temperature changing. So it really just doesn't matter.
Okay.
I'm going to read the next 2 questions together because they're asking pretty much the same thing. So one of them is, how does one find a reliable heat pump installer in Vermont? And the next is finding a heat pump contractor the next step? And where would one find one?
Yeah. Yes, that's the next step. I would go to the Efficiency Vermont website and look at their list of approved contractors. I don't know the local contractors well enough to make a direct recommendation. I haven't worked with them long enough, or I have no direct experience with them, but I would say, Efficiency Vermont vets them. They do quality control on their installations, and they have proven, with some experience that they know what they're doing and they're doing this right.
Great. Thank you. Going back to the filter question, you mentioned that there is a filter, but is it truly a HEPA filter?
Yes, it is. They are HEPA filters on these units.
And then related to the filter as well, kind of, is there any annual maintenance required for heat pumps aside from the filter?
Yeah, you probably want to do once every year or 2, open up the outdoor unit and clean off the dust and stuff on the coils. The outdoor unit, typically you can do a service plan for that with the contractor, just like you have a service plan for your oil or propane. If they come every now and then and clean the propane, the oil head that's spurting in the aerator there. Yeah, so there's pretty mild annual maintenance. Heat pumps you could probably get away with biannual, but most of the contractors will try to sell you on an annual plan, and it's not bad to do that. It's not that expensive.
Okay,
great.
That was our last question. So for anyone watching, I've just posted the link to Efficiency Vermont's website in the chat. They've come up a few times tonight for rebates and also for locating a contractor. So you might want to check that out. And I can also send it in the follow-up email to this presentation. I guess this is something I think that we had talked about previously, Matt, but maybe we just want to throw out there that for folks who are hoping to really excited maybe and want to install a heat pump like this week, you have a realistic expectation of what kind of busy people are right now.
Yeah, so I know one of the more popular heat pump folks in the Upper Valley is over a year backed up in doing installations. So right now the contractor world is catching up to the demand, and there can be long waits. That's not true for every company out there, right? I have heard some other companies that are able to come and do it, within a month or within a couple of weeks, but you might have to seek to find someone who can do it immediate versus someone who has a backlog. I will say, traditionally for HVAC, their heavy season is the middle of the summer and the middle of the winter. And in the fall and the spring is where they're typically least busy. That's often the best time to get their attention. So right now might be a great time to get someone's attention. They may have bandwidth before they're doing emergency calls in the winter.
That makes a lot of sense. There's a question here, will the recording be available soon? I should be able to send it out tomorrow, barring any glitches on my part. But yes, I should be able to send that to everyone who is signed up for this tomorrow. So you've got a thank you here for sharing so much info. And then we have another question, actually. Is there a need to ramp up training for more installers in order to meet demand for heat pumps?
Yes. And one of my jobs is training contractors. It's all it's a big portion of my work right now. Although, sorry, I do that in New York. So.
Yes, do not call Matt asking him to install your heat pump.
Yeah.
He will not be able to.
But I know Jake Marin and Lee Ling and the folks in Efficiency Vermont. I work with them professionally. We're colleagues on some level. They have the same thing, and they're working on the same. They're trying to get new contractors. They're doing training programs. There's a lot of work to sort of train up more folks and expand that market. But right now, there's catch up. Demand versus supply is mismatched.
Oh, we have a last minute question here. Are heat pumps still using Freon?
So heat pumps use a refrigerant, and refrigerants do have their own global warming potential issues. R410A is the current refrigerant. I can't remember its CWP. It's not Freon, but it is a refrigerant that has its own issues. It is hermetically sealed in a loop. If they don't do their job well, it can leak, and that is a problem, and that has to get replaced. So make sure that they're professional and they seal their refrigerant. They do a refrigerant charge test, and they do a refrigerant leakage test, which they should do on every unit they put out. Basically, everywhere you have a connector, you got to make sure you did that connection really well. And that's a technical skill that a lot of new folks or less experienced folks can get wrong and can mess up on. So it's worth checking. I do believe Efficiency Vermont does quality control checks to make sure that's working well. So there's a little bit of peace of mind that if you get checked, but yes, it does use a refrigerant. I will say the feds are changing the rules starting in 2023. There's going to be a new refrigerant, R23, that's much lower global warming potential as mandatory. So if you wanted to wait it out for that, but the global warming impact of the refrigerant is real, but also not that problematic, because if they do their job right, it's sealed in a loop. It does mean, though, when you get rid of your heat pump, if you're decommissioning, if you're getting rid of it, make sure they capture that refrigerant before they get rid of it. They collect it back out so it doesn't leak into the environment.
Okay.
Well, thank you, Matt. It was great.
Yeah, thank you so much, Matt. That's been really informative, and people are thanking you in the chat. So that's really awesome. Thank you to everyone for coming. I just realized my answer to the question previously was a little partially incorrect. I've also been on Facebook Live for this whole presentation. So if you do want to watch a recording or you missed a part, you can actually go to Sustainable Woodstock's Facebook page and watch some of this if you have a Facebook account. If not, it's okay, and I'll send it tomorrow. So just clarifying there. But yeah, really can't thank you enough, Matt. That was really informative. I learned a lot. So we'll follow up by email to everyone.
Thanks, Jennifer. Thanks, Michael. And thank you to the audience.
All right. Have a good night.
Bye, everybody. Thanks for joining us.